Welcome to Ask and Learn.
So given the sequence AN, we define the positive and negative terms by these two formulas here. So let's go ahead and show part A here. So we're given that this sum is absolutely convergent. And we'd like to use that to prove that these two series of the positive terms and one for the negative terms, that these are also convergent. So let's go ahead and prove that. The proofs will be very similar in part A of both of these facts here. So starting with the first series, just use the definition of AN plus up here to rewrite our nth term. And I'll do a step further. I'll go ahead and split up these fractions here. Now, because AN is absolutely convergent, that implies that the sum of the absolute values and the sum of AN both converge. So I can go ahead and actually rewrite this as the following. I do AN, pull out 1/2, and distribute the sum inside, and also pull up the 1/2. And as we just said, absolute convergence implies that the sum of the absolute values converges. And by comparison with this green series over here, if you use comparison test, let me write that out there, that's an important step, that'll also imply that the sum of AN also converges. So in general, absolute convergence implies sum of absolute value and the sum of AN both converge. So that means that these sums are real numbers, and if you divide them by 2 and add them, you still get a real number, so the whole sum converges. Now in part B, or excuse me, in the second part of part A, we'll deal with the minus term. Oops, it should just be a minus, not a -1 there. Once again, you can go from 1 to infinity. And I use the same steps as in the previous line. You get the same thing except minus sign. However, the fact is, if you subtract two convergent series, you still get a real number. So since both of these sums converge, this is a real number, so it converges. And so that resolves part A. We showed both of these sums converge. Let's go on to part B. Now we'd like to show that if AN is conditionally convergent, and I'll remind you what that means in a second. We'd like to show that this implies that those sums that we just considered, they don't converge, but they'll diverge in this case. So conditionally convergent, that means that AN converges, but if you take the absolute value on the inside, that'll diverge. So that's the definition of conditionally convergent. And if we write down those previous equations we had on the previous page for our two sums that we're considering, so let's go ahead and write those back out. Now, using the fact that we have conditional convergence, this first sum will converge here, so that is a real number. However, the second sum diverges, so this will be infinity. And if you add infinity, in other words, if you add a divergent to a convergent series, the result will be infinite, not a real number. So this diverges. And similarly, if you do the one with the minus sign, this time you'll have a real number minus infinity, so this one will also diverge. Let's go ahead and pull out the 2, 1 to infinity. So this converges, but then this one diverges to infinity. So you have a real number minus infinity, that'll be minus infinity, so that this sum also diverges. And that resolves part B.